We will start with the definition of power dissipation or conversion in a circuit where loads are connected in parallel. The power dissipated across each resistor can be calculated by using the given formula. So for instance, these are the loads R1, R2 and R3. The power dissipated can be calculated by simple formula, which is V square by R. Now we can add up the power absorbed by each load, and the total power will be equal to this. Now at this point, an interesting thing pops up, that what if we want to know for how much time the given power continued. For that, we use a unit which is called watt second. However, the value in watt second is very small, so we convert it into kilowatt hour. Kilowatt hour, which is also called a unit and is used to determine the amount of electric bills. We can take an example by considering R3 as a bulb, and if we leave it on for 12 hours, what is going to be the cost calculated at rupees 10 per unit. This is just a simple example. So what we do is, we first of all, we know the power absorbed by P at R3 was 720 watts. We convert it into kilowatts, and then this is going to be multiplied by the number of hours it remains switched on, and the product is going to be multiplied by the cost, which is rupees 10, and this is the amount of rupees you're going to be spending for that bulb to remain switched on for 12 hours. So this is just a simple calculation and simple example. Now let us take another example of a pure resistor connected across an AC supply. We know that in AC system, voltage and current are functions of time, which means they are periodic in nature, and at different point in times their product, which is the power, will be of different values. So what we do, we measure the instantaneous power by multiplying the voltage, which is written here as Vm sine omega t, and the current flowing, which is Im sine omega t, where omega t represents the frequency. Now if you look at the plot, it can be seen that the voltage and current are in phase. The black line, the black waveform, and the dotted waveform, they both are in phase. To draw a phasor diagram, consider voltage as reference. We draw this phasor in this direction, which is V. And since there is no phase difference, the current is going to follow the same direction as of the voltage. So this is the phasor representation. The power dissipated in the circuit, which is the product of V and I, which can also be seen in the graph. You may notice that the power does not go negative, because in negative half both current and voltage are negative and the resultant power is positive. So our power is going to stay positive when we have a pure resistor as a load. Moving on, we know that the power consumed in a circuit is classified into two types. First is instantaneous power, which we just calculated, and the second is average power, which is calculated over the entire cycle. If we expand the instantaneous power, which was, let me write it down, which was P equals to Vm Im by 2 1 minus cos 2 omega t. Okay, so this was the instantaneous power. If I segregate into two parts, that can be written as Vm Im by 2 minus Vm Im cos 2 omega t by 2. So to calculate the average power, we have to take the integral over complete cycle, and taking the integral, that is going to be P capital, the average power is going to be equal to 1 over 2 pi integral, which is going to be for the complete cycle, is Vm Im by 2 d omega t minus 1 over 2 pi integral 0 to 2 pi Vm Im cos 2 omega t by 2 d omega t. So after solving it further, the first part will return a value which is going to be equal to P equals to Vm Im by 2, and the second part will return a 0. So the net power is going to be Vm Im by 2, which is also written here. Now if we look at the plot and see the power curve, the average power stays constant throughout the cycle. Okay, now we understand the concept of instantaneous and average power for a resistive load. Moving on, let's talk about an AC circuit with an inductor connected across a supply. We know that the AC supply is Vm sin omega t, and the energy flowing in the circuit will be stored in the inductor, and that is going to be in the form of a magnetic field, and which is also going to oppose any sudden changes in the rate of flow of current. We know that. So to derive the current, let's say the induced EMF is LdI by dt. We are all familiar with this. Okay, and that can also be equal to the voltage. Okay, and if we substitute this voltage by Vm sin omega t, we can compute the value for I. Okay, so for maximum value of current, the sin omega t will become 1, and we can write it in the form like this. Or for example, let's just not go there. We first take the integral. So after taking the integral, the expression will be something like this. Minus cos omega t, and this can also be written in the form of sine, and in that case it will be Vm omega L sine omega t minus 90. And again, which I was saying before, that for maximum value of current, this portion, let me change the color, this portion is going to become 1, and I will be equal to Vm over omega L. And that can also, if we substitute the value of Vm, the I can become I am sine omega t minus 90. So this is how we can derive the function of the current. The expression is derived. Okay. Now what we do is we try to draw the phasor with reference to the voltage. We can see from the expression that the current lags the voltage by 90 degree. We know that already. So that we draw the current phasor in the negative direction. You see, this is the voltage reference and this is the current phasor. Okay, that's done. Our next step is to find out the power consumed in a circuit. The expressions for instantaneous voltage and current are given, which are these two. Okay, now we take the simple product. We come up with this expression. This is this, and can also be represented in the form of RMS, which is the final expression for the instantaneous power. Okay, so if we look at the plot, we can observe that the voltage starts ahead of the current, and considering the value of power at different instants, we see that the value of power only stays positive for positive values of voltages and currents. You see, in this part, the value of current and the voltage stayed positive and the resultant power was positive. And similarly, in this part, let me change the color. In this part we had positive voltage but negative current. So in this section, when you take the product, the current is going to, the power is going to be negative. Okay, so that's understood. And that also means that the positive power is the power which is stored by the component, and the negative power is the power which is released by the inductor. And we can also say that the energy taken by the inductor will be returned back into the other half of the cycle. So instantaneous power is calculated. Now we are going to move further and try to calculate the average power. So the average power is the integration of the instantaneous power over the complete cycle, and after we integrate that, the instantaneous power, the resultant average power is going to be 0. And this also justifies this concept here that for a pure inductive load, the energy stored is going to be equal to the energy released. That means the average power is going to be 0. Okay, now quickly moving to the next circuit, where we have a resistor connected in series with the inductor. The supply voltage is Vm sin omega t. Yes, and the supply voltage is Vm sin omega t, and the voltage across the resistor is going to be Vr, and voltage across the inductor is going to be VL. Now looking at the phasor diagram and taking VR as reference, the current will follow the same path of VR, which is this, but at the same time it will be lagging the VL by 90 degrees. So current, we know that current lags the voltage for a pure inductor by 90 degrees. So this is how the phasor looks like. And this also shows that the angle between the current and the total voltage is some degree phi, which is unknown at this point. This is the angle between the current and the total voltage. With this assumption, we write the equation of I, which is the instantaneous current. Current is this: I am sin omega t minus phi. Okay, considering this as a right angle triangle at this point, what we do is we can say that the V square can be equal to VR square plus VL square. and that can also be written in terms of the product of current and the resistor and current and the inductive reactance. Okay, and in that way we can write down the expression for maximum current, which is Im equals to V by R, or V by impedance, and impedance is the square root of the squares sum of the resistance and the inductive reactance. So V by impedance, and if we substitute the value of V with Vm sin omega t, the final expression would look like this, which is Vm sin omega t by impedance, or this can be equal to Z and Vm sin omega t. Okay, we know that. Cool. To compute the value of phi, which is the angle between the current and the total voltage, again consider the right angle triangle, this one, the phasor diagram, and if you take the tan of the angle, tan phi is going to be equal to VL by VR, and value of angle is going to be equal to tan inverse of VL by VR. And if we put VL equal to IXL and the VR equal to IR, I and I can be cancelled out, and the same expression can be written in the form of reactance and resistor. Okay, now to plot the curves, consider the green waveform, this, as the voltage across the resistor, and the blue waveform is the current IR following the same path, this. Okay, now talking about the inductor current, which is IL, it lags the voltage by 90 degree. So this current here is the inductor current, and it lags the voltage by 90 degree, that we already know. But for the case when we have a RL load, the current IRL will slightly move back and is shown in the red color, this waveform. So this is the waveform for the current in a RL load, for a RL load. Now to calculate and plot the instantaneous and average powers, we know the formula, and by solving the trigonometric equations we can come up with the final expression, which is this. Alright, now to calculate the average power of the complete cycle, we know that we will integrate the expressions from above and solve, which will eventually give us the final expression in the RMS form. And if you look at the plot and if you observe it, the negative halves, which are these two, the negative halves are smaller than the positive halves, which means that there are some power losses associated with the circuit. Okay, so now moving on to the next element, which is the capacitor. In case when we have a pure capacitor connected across a power supply, the concept is almost the same as of the inductor, but in this case current is going to lead the voltage. Simple. As seen from the phasors, you can, if voltage is the reference, then the current is going to be leading the voltage by 90 degree. Okay, the AC voltage again can be denoted as Vm sin omega t, and when the current flows in the circuit, you know that the capacitor charges and discharges at the same time. In that case, the current can be represented as I equals to dq by dt. Okay, and where the charge is defined as q equals to cv, we know that, or if we substitute the value of v, q equals to c Vm sine omega t. Alright. Now what we do is we put this value of q in the expression of I, which is the instantaneous current, can be written as d by dt of Cvm sine omega t. Okay, which can also be written as, if we take the differential, it will become omega C Vm cos omega t, or in the form of sine, it can simply be written as omega C Vm sine omega t plus 90. Okay, that is simple mathematics. And we know that for maximum current value, which is Im, this portion will become 1 for the angle of sine, and Im can be equal to omega C Vm. Okay, and substituting the value of Vm and Im in this expression, which is on the top here, I can become Im sine omega t plus 90. Okay, so we just substituted the value of Vm, and this is the final expression of the current. Okay, now we have computed the current. Let us calculate the power dissipated in the circuit. The expression for instantaneous power is given in the RMS form, which is a simple product of the instantaneous voltage and current. Similarly, if we move further, as of the case in pure inductive load, the average power here for the capacitive load is calculated to be 0, which again means that the power stored by the pure capacitor is equal to the power released. So this concept is also verified for a pure capacitive load. Now what we do is we add a pure resistor in series with this capacitor. By looking at the phasor diagram, we can tell that the VR is taken as a reference here, and the current follows the same path, which is also leading the capacitor at the same time by 90 degrees, this portion. And since the phasor is in negative direction, it can be represented as minus Vc. Okay, now that shows the current at some specified angle with respect to the total voltage, which we considered in the case of an LC of a RL circuit. So there's a angle phi between the total voltage and the current. Now again, from the Pythagoras theorem, if we consider this triangle, we can say that the V square can be equal to VR square plus minus Vc square, and that can also be written in form of the product of current and the resistor, or the capacitive reactance. And from there we can calculate the expression for Vim, which is V by impedance. Okay, and by substituting the value of Vm, the final expression for Im will be this. And if you want to compute the angle, which is phi, again we take the tan of angle, which is minus Vc by Vr, and the expression for the angle is going to be this, or like this. Now if we look at the plot, we know that this is the input voltage, fine. And in case of a pure capacitive load, the current leads the voltage by 90 degree, which is somewhere here. Okay, that we know already. But in the case when we have a RC load, this waveform, the one in blue, will slightly move back somewhere here. More like this. And this angle is going to be phi. So this is going to be the current in case when we have a RC load. Okay. Now to compute the instantaneous value of the power, we will simply take the product, and by solving the quadratic equation as like previous cases, the final expression will look like this. And again, the average power is the integral over the complete cycle of the instantaneous power. We are taking the integral here, and the final expression will be equal to this, which is that we in the form of RMS voltage and current with the angle cos of phi. And this is exactly equal to the case when we discuss RL load. So the average power of a pure RL load and pure RC circuit or load is equal, which is Vrms into Irms cos of phi. And if you again look at the plot, you can see that, okay, let me highlight it, that this section here, the bottom, the negative halves, are smaller than the positive halves. That means again is a little power loss happening in this circuit, and that is definitely because of the R or the resistive component in that. Okay, I just recognized that I made a little mistake here with the current waveform. I'm going to correct it. So let me redraw it. So it will be shifted back to the degree phi and will follow this path. So this is the current when we have a RC load in an AC circuit. Okay. Now moving on. Before we move on, let us just summarize the discussion we just had, that how phases are plotted for the resistive, inductive and capacitive loads. We understood that, and the instantaneous and average powers were also computed. Another application of the use of vectors is determining the total opposition of an AC circuit to the flow of current, and this total opposition is called impedance, which is this, and they measured in ohms. It is a complex quantity made up of real and imaginary reactance. Similarly, the apparent power is also a complex quantity which consists of real and reactive power. And if we take the square root of the square sums of these two, we can come up with the magnitude of the apparent power. So let's start with the active power, which is also called real power. For instance, if you consider a circuit and measure the voltage and current separately with two different meters, the simple product is going to be the apparent power, but the power measured with the wattmeter gives you the real power. This real power is actually the power converted into some other form of energy, or in case when we have a resistor, it is going to be in the form of heat. So the power equation when we have a resistor is going to be this, I square R or V square by R, and the unit is watts. And there's a little note underneath that the voltage in the above equation is the voltage drop across the resistor and not the entire circuit. Moving on, reactive power is the power which results from an inductive or capacitive reactance, and it circulates within the circuit. The expression here looks similar to that of active power, but it incorporates reactance instead of resistor. So again, the voltage drop across that component is going to be equal to this, and that is not going to be the entire voltage drop in the circuit. And the reactive power is negative for a capacitor and positive for an inductor. The negative concept actually comes from the concept of when we discuss RC phases, and we saw that the phasor was in negative direction, and that is why we have a negative here. Moving on to the apparent power, we have already discussed that it is the product of voltage and current, and the unit is VA, which is V times A. Sorry, I forgot to mention the unit of reactive power, that is VAR. And it is again mentioned that apparent power is the product of V and I, and these are not phases. This is just the magnitude. Here's the famous power triangle, which is only valid for balanced systems. This we will study later in the course. And by applying Pythagoras theorem on this triangle, apparent power can be calculated by taking the square root of reactive and active power. Okay, so if we further consider this triangle and we take the cosine here, the cosine of theta is going to be equal to P over S. So, and generally if we look at a circuit, it is usually desirable to know the ratio of real power converted in a circuit to the apparent power, and that ratio is called power factor. So this ratio can also be called power factor. Okay, and that also means the power factor can be represented as cos of theta. We understood the concept of power factor, what is power factor, and now we would discuss some features of power factor. So it says that the power factor serves as a measurement to check how well the electrical equipment is performing and converting the given power into something useful. The higher the power factor, the higher the efficiency is going to be. Similarly, let's take an example of a power distribution system which offers low power factor. That is definitely not acceptable, because the consumer would never want to deteriorate the health of its households or any other electrical equipment. Similarly, low power factor could also lead to voltage drop in a distribution system. So these are few features of the power factor. In this slide, this is the simple representation of a power factor when calculated for pure inductive or capacitive circuits. And it completely depends on the degree of phase the current lags the voltage or leads the voltage, which is cos of phi. And it says that the inductive circuits have lagging power factors and capacitive circuits have leading power factors. And since this is a leading power factor, in most of the applications when we see phase difference, what we do is we try to introduce some capacitive element, and that actually helps out to improve the power factor. There we are going to study in the later lectures. Okay. In this last slide, the concept of addition of individual active and reactive powers at certain point on the network is shown. Here, or a circuit is shown. It says that the total real and reactive power is the sum of powers at each circuit element. So you sum up the active powers and you sum up the reactive power, and that is going to be the accumulative sum. And in this case, the configuration, the connection configuration does not really play much role here. So with that, we understood the concept of the circuits, where we had resistor, inductor, and capacitors as elements, and afterwards we understood the definition of power, active, reactive, and apparent power, and the power factor and the features of power factor. Now with that, I would like to conclude my lecture here, and in the next lecture we will be discussing the three-phase power systems. Alright, see you next time.